let's talk speed of sound. So, speed of sound. So, the first thing is sounds are caused by a vibrating source, okay, that sends waves out through the air. Okay, so the medium that sound travels through is generally the air. However, you can also get sound traveling through water and even through solids. So essentially, to be a sound, we would consider it to be within the range, or have to consider it to be within the range of human hearing. Okay? And the human the human can hear between a frequency of 20 hertz roughly up to 20,000 hertz. Okay? So we will just pull up a little sound generator and see if we can run through that frequency range. So frequencies outside this range, and you can just go online and find yourself a little frequency generator and test this out. If it's above 20,000, we call it ultrasonic. Your ears cannot hear it, okay? And below here, we call it subsonic, okay? So this is the frequency range that, that people can hear. All right, so now, what is sound? Well, sound is simply, and we'll use a speaker cone as an example here. So a speaker cone basically is just like a paper or sometimes like carbon fiber or some other material in a cone shape, all right, with on the back a coil, okay, and then it's got a big magnet on the back here, okay, and basically what happens is current gets turned on and off in here in time to the music and to a higher and lower level. And what that does is it turns the back of the speaker cone into an electromagnet. Okay, so basically you send in more or less a wave of electricity, and that causes the speaker cone to move back and forth. Okay, there's various other ways to generate sound, but they all have to do with some vibrating medium, right? So if you've got a drum and you bang the drum, okay, the drum head vibrates up and down, and this emanates sound waves out into the air. All right. Now, if you look, these are going to be longitudinal sound waves, right? Based on whether this is moving forward and pushing molecules together or pulling back and rarefying them. So essentially, you've got areas of compression, right, where the molecules of the air are pressed close together. And you got areas of rarefaction, where they are spread apart more, right? Okay, and these travel out, and then over here somewhere, your ear acts like an antenna for this. So you got the tube leading into your ear hole, and in the back, you've got a little membrane, okay, called your eardrum, that is then attached to like little bones, okay, and as these compression waves go in the ear hole, they vibrate this guy back and forth in the same frequency, and your brain then interprets it as being sound, okay? So outside the range, either it's not going to be able to vibrate your eardrum or you're not going to recognize it as sound. Okay, so that's kind of the mechanism of how we hear and how, you know, energy from one place can move to another through the air. Okay, the speed at which sound moves is dependent on the medium it's traveling through. Okay, just like any other mechanical wave, it's dependent on the medium. All right, this medium, for the most part, is going to be air. Okay, and to change the medium of the air, or to change the air itself, you could do a few things. You could change the humidity, the pressure that the air is at, right, the atmospheric pressure, and the temperature. Can't really change the nature of air, although I guess if you like had, say, helium or something like that, the sound would travel much faster through helium due to the fact that the molecules of helium are much lighter. And you've probably heard that where someone has inhaled helium and talked, and they get a high-pitched voice. Okay, so it raises the frequency, or vice versa. Heavier ones like sulfur hexafluoride, for instance, lower the voice. But in regular air, you get a little formula that looks like this. The velocity of sound is equal to 331 meters per second plus 0.6 times the temperature. Okay, so we'll use this in an example. Oh, and this is the temperature in Celsius. Okay, and this, of course, will be in meters per second. All right, so example. Find velocity of sound at 20 degrees C. Just for us, we don't really consider this. Just to be aware that this is not like a perfect formula, but it works quite well. We'll do a little experiment where we can actually see it. It's pretty close to right on. Okay, so find velocity of sound at 20 degrees Celsius. So velocity of sound then would be 331 meters per second plus 0.6 times 20. So essentially you get this. Velocity of sound is 331 meters per second plus 12. And 343 meters per second. Okay, this also works for negative temperatures as well. So if at 0 degrees, then we could say that this is 331. Okay, at lower temperatures, it would of course be lower, and at higher temperatures, it would be higher. This might be counterintuitive because you might say, but on colder days, the air is more dense, the molecules are closer together, which is true, but they're also moving more slowly. And the passage of sound requires one molecule to hit into the next, to pass that longitudinal wave along. Okay, so the colder it is, the less likely the molecules, or the more time it takes for them to strike the next molecule over. So I just want to quickly look at this formula graphically. My assumption is that it was come up with from experiment, although it's possible you can derive it through basic principles. But essentially, you would do this if you want to kind of get that. Okay, so you're going to make yourself an axis, and what you're going to do is you're going to go out and you're actually going to measure sound. Okay, and one way to do this would be to say clap. Okay, and wait for the clap to bounce off a wall and echo back, and do some timing. Do a little bit of math and figure out the velocity of sound. And do this at multiple different temperatures. That's one way I can think of to do this. Now what you're going to find is you get essentially a linear relationship on your graph. It's going to look something like this. Okay. So what does this represent? Well, what we're saying here is you've got temperature on this axis, okay, on your x-axis, and you've got speed of sound on your y-axis. Okay, so you get your speed of sound here. This value, this is going to be your y-intercept. That'll happen at 331. Sorry, my mistake. That will be 331 meters per second, and it'll happen at 0 degrees Celsius. So that represents 0 degrees Celsius. Okay, so as we go up in temperature, the velocity of sound goes up. Okay, so the velocity goes up in time. And as we go down in temperature, the velocity also goes down. Okay, for math class, you know this, y equals mx plus b. Okay, so in this case, your y-axis is the velocity of sound. M is 0.6, see where that comes in? Your x value is your temp plus 331. So essentially, it's just that formula. We just put it in a different way of looking at it. So M, where does M come from? Well, it's the slope of a graph charting temperature from the real world. That's where 0.6 comes from. Okay, it's unitless. It's just the slope of this line. I guess actually, technically, it would have the unit of inverse temperature, I guess, because you got to get rid of degrees Celsius and end up in meters per second. Okay, you don't need to get all that technical with that, but that's essentially, I guess, what it would have to be. Your x value here is t. Okay, it's the independent variable, and this is the dependent variable that depends on it. And this is just your intercept, right? What happens when temperature is 0? Well, it's at 331 meters per second. Okay, so that's the background as to where that would come from. It's the result of experimenting and figuring out the mathematical relationship between these things. Okay, so we're going to leave it there.